let me just quickly explain Newton's second law and then we can get back to our maths. So Newton's second law is basically this. There are lots of variation, but overall it boils down to this formula. So the force acted on a body is proportional to the product of its mass and its acceleration. So what that means is, well, the force acted on a body, this is F here, is proportional to the product. Product means two things multiplying with each other. So the product of its mass and its acceleration. Okay, so what that means is let's look at this scenario here. Let's imagine we're looking at a car on a road. Let's say the mass of the car is 5 kilograms. I know it's a bit silly, but let's just imagine it should be a lot heavier. But let's just say it's 5 kilograms. And the force, if you push this car, the mass of the car is 5 kilograms. Let's just say you push this car at 10 newtons. The unit just know that the unit of force is newtons. Just say let's just say we're pushing this car with a force of 10. Okay, and the mass of the car is 5. Now, if you put this into here, F in our case would be 10. The mass of the car is 5. So the acceleration, we can work out the acceleration. So divide both sides by 5. That will give you 2. So A here equals 2. So what that means is this car will accelerate at 2. Well, the unit of acceleration is meters per second squared. I've explained this in one of the earlier videos. So if you don't understand it, scroll back. So the acceleration of this car is 2 meters per second squared. So what that means is well, remember our acceleration time graph, our speed time graph, and our distance time graph. So what that means is when you apply a force of 10, the acceleration of this car will be 2. So the acceleration here is 2. Okay, that means the speed will keep on increasing like that, and then the distance covered by the car will be something like this. It will be a quadratic. Okay, so the force acted on a body is proportional to the product of its mass and its acceleration. So if you increase the force, let's say 20. So if you put 20 into the F, and then the mass of the car is always the same. 5a. Well, the bigger the force, the bigger the acceleration. So a here equals 4. You see, the bigger the force, the bigger that's what proportional means. The force acted on a body is proportional to the product of its mass and its acceleration. So increase the force, you increase the acceleration. Okay. Now let's keep it at 10. Let's keep the force constant. Okay, make it 10 all the time. So now let's look at a bus. Let's say the mass of the bus is, I know it's a bit silly, 8 kilograms. Let's just say it's 8 kilograms. So if you have a force of 10 and the mass of the bus is 8, then put this 10 into the F. So 10 here, and then put the 8 into the M. Now the acceleration here will be 10 over 8. So here last time it was 2. The acceleration time graph was 2 for the car. Well, the acceleration here would be, well, divide top and bottom by well, even number. So that equals 5 over 4. Okay, so it's just over 1. So somewhere here. So the acceleration of, you see, what I'm trying to say is that if the mass increases, then the acceleration decreases. So for the acceleration for the car here is 2. The acceleration for the bus here is 1 point something. Okay. Now look at let's say a motorbike here weighs less than 5 and less than 8. Okay. So the mass of the motorbike here is 3. Now F equals ma. So now put the 10 into the F. So this will be 10 equals, the mass is now only 3. You see, because this motorbike is lighter, the acceleration is 3 point something. Okay, so you see, decrease in mass, the acceleration increases. So if you look at the acceleration time graph for the car, it would be this. For the bus, it would be somewhere here. For the motorbike, it would be here. Now, if you look at the speed time graph, now speed of the car, let's say is something like this. Now, the speed of the bus would be something like this. The speed of a motorbike would be something like this. It would build up speed a lot faster. And then if you look at the distance traveled, for the car, it would be something like this. For the bus, it would be something like this. For the motorbike, it would be something like this. Okay, so the distance covered would be a lot more for the motorbike. For the motorbike. Now let's look at this here. Let's say you're at the traffic lights here. You've got the motorbike, the car, and the bus all lined up. Now, assuming that let's say that the engine will be the same for all 3 vehicles here. That means the force will be the same for all 3 vehicles. Now, as soon as the light turns green, the motorbike can accelerate a lot faster. It's easier for the motorbike to accelerate away a lot faster. Then it would be for the car, and then the bus. It takes a long time for the bus to accelerate. Okay, because of Newton's second law, F equals ma. Just know that the force is proportional to. Don't worry about this proportional thing. I will explain it another time. Proportional to the product. Now, product means 2 things multiplying with each other, to the product of its mass and its acceleration. So if you keep the force the same and then you increase the mass, then the acceleration will decrease, just like the case of the bus. Now, if you make the mass small, then it's easier for something to accelerate, assuming that the force stays the same. Now, I don't know if you're aware of this, but sunlight, if you have a bathroom scale here, sunlight is actually giving it a push. So it might not be very much. It's a microscopic amount, but it does push the scale. The sunlight does actually push this. It's actually pushing the bathroom scale here. So what you know on Earth, if you have wind, it pushes a sailboat here. Well, in space, you can have here you've got a sail here. In space, you can also have a solar sail. So that means in space there's no friction. So you can actually build a solar sail. So meaning that sunlight can actually push this satellite, if you like. It won't be very much. It's a tiny microscopic amount of push. So that means there's a force. Okay, F equals ma. So there is a microscopic amount of force on this satellite. Now, if there's a force, if there exists a force, then the mass of this thing will be the same. So if there's a force, then there's going to be an acceleration. If there's a force, there's going to be an acceleration. Even though it may be heavy, this thing, there will still be an acceleration. But the thing is, our acceleration here is tiny. Tiny. Well, let's look at this here. Acceleration time graph. Now, this we are using the sun's light to push this satellite. So, there's a force on this satellite. Meaning, from Newton's second law, if there's a force, then there must be an acceleration. Okay, so the acceleration might be microscopic, might be a really small amount. Okay, let's say 0.0000. Let's say something like that. Now, remember our acceleration time graph. Well, we've got the speed time graph. Now, okay, the acceleration is small. Granted, the acceleration is small, but then the speed is always going to increase. Okay, it might be a very shallow gradient, but the speed is always increasing because there's a force. Because there's an just remember, if there's a force, then there's an acceleration. Now, if there's an acceleration, there's going to be a gain in speed. Okay. Now, if there's a gain in speed, then your distance time graph will look something like this. It may be shallow, but it's climbing a lot faster and faster and faster. What I'm trying to say is that even though the force here is really small, and well, if there's a force, there's an acceleration. Even though the force is small, the acceleration will be small, but then the speed will always increase. Now, if the speed increases all the time, then the distance covered will climb a lot. So okay, this satellite will be slow at first, but over a period of let's say a week or a month or a year, remember this is time here. As time goes on, let's say a week here, let's say a day here, a week here, a month here, a year here, and let's say in 5 years' time, the distance covered will be a lot because the speed increases each time. So what I'm trying to say is that even though the force is really small, over a long period of time, this satellite can travel really fast. Okay?